I consider myself as a computer scientist, but in the meantime, I was trained in control theory. I also consider myself as a control theorist and a statistician. So, I mean, I'm very nervous to talk about like general advances in the field. So I wanna like put on my hat as a theoretician. So I'm going to talk about like on a high level what are going on, what are exciting problems, and what are open theoretical questions that would really need help from mathematicians. We have been really witnessing this amazing explosion of technologies, and I mean it's really like a daunting task for me to like open up Twitter every day, and then there are like tons of new papers and people are tweeting about new research. It's just incredibly hard to keep track of everything. I don't know if you share similar feelings. Okay, so research is exploding, okay? So the very beginning notion of generative AI might be rooted, not really rooted, might be dated back to really only a few years earlier, maybe from variational autoencoders, okay? But then we have seen transformers, we have seen different models applying to different tasks, to computer vision tasks, to text generation tasks. And then we saw ChatGPT, we saw Stable Diffusion, we have ChatGPT 4.0, we have Gemini, we have Cloud, we have Perplexity. So everything's sort of like popped up, okay? Today my homework is to talk about the two most important models today, which are changing our daily life, okay? So the first model is autoregressive models for language generation, okay? So it works by generating languages token by token. We can think about this model itself is really a Markov chain, okay? And tokens are discrete in nature. So this is model number one. And model number two is for generating continuous data, for generating continuous contents. So this is the so-called diffusion models, which is the model that would generate images, audio data, video data, even protein structures, architectural plans. Okay, so diffusion models was supposed to be more about generating continuous object. But actually the boundary between the two is actually getting blurry. So people are using this for that and that for this, and maybe the hybrid would work out the best. Okay, let's talk about large language models first. Okay, so as a statistician, usually people care about statistical rates, people care about asymptotics, okay? So if we look at asymptotics or for large language models, so the model sizes are increasing superlinearly. Okay, so by looking at this picture, which I got from the web, it's really like comparing the sun to the moon. If we compare the recent version of ChatGPT 4 to the baby version, GPT-1. So a very, very basic but fundamental question is there a scaling law for large language models? And this is a first order question a data science researcher would ask for basically for any data intensive task. Okay, so the first question is, okay, if we have 10x or 1000x more data than we currently have, what can we do? Okay, so one may ask, does that data even exist? So it turns out that the current best large language models we're using today are only trained on less than 1%, actually less than 0.1% of all available text data generated by humans. Okay, so the models are not even close to using up all the data. So it is indeed possible to use 1,000 times more data to train a model. Okay, so then we care about the scaling loss. So the typical loss function people use for training autoregressive models is cross-entropy loss. So you can imagine it's some sort of like log likelihood. Okay, so that's my loss function there. So researchers actually try to play around with models of different sizes to try to actually plot the scaling curves. Okay, and empirically, they actually fit their curves to figure out a power law. Okay, which is right there. Okay, so here the notations are actually just very different from typical notations in statistics. In statistics, D usually stands for dimension or like model sizes, and N for sample size. But here, N stands for the number of weights in the large language model, and D stands for number of tokens in the data set. So we are just flipping the notations. Okay, so it turns out we actually have a pretty nice power law. Okay, so in typical like finite dimensional statistics, we would expect something like 1 over D to the power of 0.5. But now we have D to the power of 0.28. Okay, we don't really know what that means, and theoretically, there's no explanation to this. Okay, and also there's a magic number 1.69. So this is the intrinsic perplexity. This is due to intrinsic stochasticity in human languages. So there's some like bottom level that we can never cross. Okay. So people came up with this estimate and use it as a guideline to figure out how much bigger they need to scale up their models and how much more data points they need to collect and clean up for training the model. People also try to figure out how the amount of compute is supposed to scale with additional amount of data and error tolerance. So here, flops is going to be measured by the number of floating point operations. Okay, so apparently there's supposed to be some science going on there. And this is vastly underexplored. We don't really understand why this is so. Okay, so this is really an open question to explain why the power law scales like this. And maybe there can be some fundamental breakthroughs to do better than this. So scaling laws, we're thinking about scaling things up to be really big. Now let's also think about what really goes inside those large language models, or even beyond large language models. So a very, very, very critical trend in AI machine learning research is that actually different subfields of AI machine learning, so they're actually converging to the same architecture or even the same training laws. By the same architecture, we mean transformers, which started from this very, very famous paper called Attention is All You Need. And starting from this paper, there were many follow-up papers with titles like A is all you need, B is all you need. But it turns out that only attention is all people need. Okay, so transformers turns out to be a universal model, and people are actually using transformer to beat every single specialized model in different tasks. It might not be the ultimate model, but I would say it's close to the ultimate model. Okay, and also as for for the actual training algorithm, so people have converged on basically the same training algorithm, which is ADAM, which is a particular version of gradient optimization with heuristic approximation of second-order information. Okay, and so this very same architecture and same training algorithm is basically being used for different kind of data, from video to text. And a fundamental theoretical question is, do we really understand transformers? Do we understand how they approximate functions? What can they represent and what can they learn? So this understanding turns out to be still very preliminary. Okay, so let's just take a look at one single transformer block. Okay, so in a transformer block, we have two parts, a multi-head attention and a feed-forward network. So the feed-forward network is pretty standard. So the magic happens in the multi-head attention. So there we have basically three matrices, Q, K, and V. They are going to be able to capture dependencies or even long-range dependencies in a long time series or a long sequence of tokens. Okay, and a large language model is going to be layers of such transformer blocks. Okay, so the understanding about what transformers is doing is very, very, I would say, limited. However, because we do know that large language models, ChatGPT, can understand human languages, right? So some people even use ChatGPT to analyze financial reports and try to predict trading policies. Okay, so it means that ChatGPT has some analytical abilities more than just making up stories. It actually knows a little bit about math. Okay, so one active research direction is to try to understand, can transformers approximate statistical learning algorithms? And it turns out that if we look at a particular transformer block, attention and feed forward, it turns out that a single block can approximately implement a gradient descent iteration for solving a statistical learning task. And this has been shown for basic statistical models like just linear regression, nearest neighbors, or even like modeling dependencies in Gaussian processes. So the theoretical understanding is each transformer block is actually learning a step, and each transformer block is learning one single iteration. And if we have layers of transformer block, this multiple layers of a transformer block is approximating an algorithm. And that algorithm is going to be the magic there that can learn about, it can learn to reason about numbers, it can learn to reason about classification problems under the mask of languages. Okay, so again, so all the research are very, very early, and there are tons of open questions. We don't really know about whether transformers are universal approximators. We don't know about learnability. Can we improve learnability, or maybe this is already the best model? And we also don't really understand statistical efficiencies of transformers for learning complicated algorithms. Okay. So transformer scaling laws, these are really about pre-training. Okay. So I have to admit, so as someone who is an academic, we don't really get to work with pre-training large language models in our research. Okay. So, but what we get to really work with a lot is we can actually work a lot with post-training, which is also a very cool set of problems. Okay, so for example, like once we have a pre-trained model, a very important task is to do fine-tuning in order to customize or adapt a pre-trained model for a specific downstream task. Okay, but fine-tuning usually means that we don't want to spend the same amount of resources used for pre-training to do fine-tuning, because fine-tuning is going to be task-specific. Okay, so in order to achieve parameter-efficient fine-tuning, so one very powerful technology is simply to do low-rank approximation. So the idea is very simple. It's really very similar to factor models. We're going to consider that we have a tensor of weights in a pre-trained model. But that tensor or matrix, they are going to be low rank. And now when we try to fine-tune the model for a specific task, we want to do it really fast, right? And then one can try to figure out a low rank approximation to the set of all weights and only do fine-tuning on the important factors of the pre-trained weights. And this can achieve 10x or even 100x speed up. But this also comes at a cost of, like, I would say, like, slightly lower performance, because we are not taking advantage of all the high-order information. Okay. So we recently had a paper about understanding the safety of large language models. Again, by exploiting the low rankness of large language models, we can actually zoom in and identify 3% of all neurons. And only those 3% of all neurons, they are critical for safety. So if someone want to attack a model, they only need to attack those 3%. And if we want to defend, then we want to figure out some robust mechanism to robustify those safety critical neurons to protect them. Another very cool problem is called, it's about decoding. So once we have a pre-trained model, when we use it for generation, we call it decoding. So there are different things people can do. For example, one very cool idea is called speculative decoding. And OpenAI does this all the time, okay? So when we ask ChatGPT a question, ChatGPT might not really answer us using its largest model. ChatGPT is going to have a sequence of smaller models, okay? So our prompt is going to be routed to the smaller model. And the smaller model is going to start generating. So you can imagine that for many simple questions, maybe there's no big difference, maybe there's no difference at all between the response of a smaller model and a larger model. So speculative decoding means that to figure out an algorithm that tries to delegate all the generation tasks to smaller models and only ask larger models to verify generated tokens for harder requests. And this, again, is going to achieve speed up and save tons of inference cost. But the mathematical problem is very cool because imagine that we're really trying to play around with two Markov chains. One Markov chain for the smaller model, another Markov chain for the larger model. And essentially we want to figure out a switching policy that can optimize some reward or minimize some loss. And this is a very nice optimal control problem. Okay, and this is again a problem with a lot of potential, and I think theoreticians might enjoy taking a look. So in post-training, another very important task is to do alignment. Okay, so alignment means that once we have a pre-trained model, it's going to be very preliminary. And now we want to make our users happy. So it's about fine-tuning or adapting a pre-trained model to make users happier. So this works by collecting user feedbacks, which are usually, I would say, likes or dislikes, or comparison between two responses. So if you use ChatGPT a lot, you will notice that it often pops up two answers and asks you to choose which one you like. This is about collecting ranking preference data. And based on such data, OpenAI and actually all the LMs researchers, they are going to come up with a reward model based on the ranking data, okay? And then they are going to use this reward to fine-tune the large language model by using a policy optimization algorithm. Okay, so this is actually a playground for researchers in reinforcement learning, and there are a lot of very, very exciting ideas and exciting advances. For example, a very important question is, my large language models is trained on like one type of data, right? But what humans like might be something niche or something different in terms of the support of distribution from the training data. So in terms of to do alignment, people have to account for distribution shift. And distribution shift in the context of reinforcement learning is going to create a lot of technical challenges. And this is about how to think about distributional robustness and how to figure out better algorithms to utilize data. And also, like, humans might have conflicting preferences. We might have some majority user group and a minority group. But if we simply average everyone's responses, the majority groups, the majority's preference are often going to be neglected. So we had a very recent paper about how to model heterogeneous user preferences and how to do alignment in a way to also respect the preference of minority groups. And there are a lot of very interesting things going on there. And this is actually really important because we know that Apple, Google, they are actually trying to launch LLMs for their own product recommendations. So for actual product recommendation, aligning to user preference, and personalization. This is the path to monetization. Okay, so now let's switch the gear, because I'm supposed to talk about not only LLMs, but also diffusion models. So diffusion models, they are, again, so I have to admit, diffusion models are my personally favorite machine learning models. I'll tell you why later. So one reason is it actually generates very nice art. Okay, so diffusion models is the model behind Sora for generating lifelike videos. It's also the model behind DALL-E, ChatGPT for generating images. And many artists, I think they hate the model. They want to figure out a way to watermark, to protect their patents, and to figure out ways to add watermarks in diffusion models. Okay. So in short, diffusion model works by transforming noise to a clean data point, maybe an image. Okay, so how is this like special? Okay, so before talking about diffusion models, the technology, let's look back into the brief history of generative AI. Okay, so in 2013, 11 years ago, I think that was probably the beginning of this. Okay, so at that time, there wasn't this notion of generative AI. At that time, people were still trying to come up with variational autoencoders in order to compress data into lower dimensions and then decode from the lower dimensions to decode and recover the original data. So the purpose here was really to do data compression, maybe to compress images into lower dimensions for better storage. So in other words, we can think about variational autoencoders as just nonlinear PCA. Okay, but however, as people work with variational autoencoders, they realize that, hey, now we have a decoder, and this decoder is fun. Because if we only work with the decoder, we can feed in a random low-dimensional vector as input, and the decoder would actually output something that looks interesting. Okay, so then people started to pay attention to this decoder. Okay, and later, another very promising model at that time was this generative adversarial networks, GANs. So again, GANs was a model developed for supervised learning, for classification. Okay, so the goal there is to train a better discriminator. But in order to train this discriminator, people come up with an adversarial generator to try to generate fake image in order for better training of the discriminator. And as a byproduct, so this generator turns out to be much more interesting than the discriminator. Okay. At that time, people realized that, hey, we can actually generate images that really look like the real ones. Okay. So this was the very basic idea. So now when we think about image synthesis, video synthesis, so we think about this class of models that are going to transform input noise to synthetic data. Okay, this is the so-called, this is why we call it generative. And people no longer care about those compression encoders or discriminators because generation turns out to be much more powerful and just much more interesting to work with. Okay, but compared to VAE and GANs, diffusion models is actually a revolution. Okay, so look at VAE and GANs. So we had a decoder and we had a generator, where the goal is to have a single neural network mapping noise to images. Okay, but diffusion models is different. So the idea is that I'm not trying to learn a single transformation from noise to image. Instead, we're trying to figure out a controlled path, a sequence of state transitions, starting from initial state, which are noises, and we want the output to be an image. So this is not about learning the entire transformation using a single neural network. This is about using a sequence of neural network to implement an algorithm which guides the generation along a controlled path. Okay, and in this view, you can imagine that the overall path, the overall transformation from noise to data, this is going to be like, I would say, a highly non-smooth transformation, very hard to approximate, very hard to learn. But if we think about this as a control problem, we can go along a sequence of smooth transitions. And you can imagine that every single transformation is going to be easier to learn and approximate because we can make every single transformation to be smooth. Okay. And in reality, for generating such an image, so usually one would go through 1,000 time steps of individual transformations. Okay. And now, for every single step in this sequence of transformations, we are going to use a neural network to determine the drift of every single step. And stable diffusion was the state of art 2 years ago. But in stable diffusion, the neural network was a U-net with up to 900 million parameters. Okay. So the reason I really like diffusion models is it is based on elegant mathematical principles. So the goal is to figure out a path from noise to image, which is hard. But let's look at a simple task. What if we start from images and we want to make them into noises? This is very simple. We can simply do that by adding noises incrementally to the image and eventually corrupt the original image into white noise. Okay, so this is called the forward process in a diffusion model. And if we think about the continuous time approximation, we can actually write down a single OU process to describe it. We can make a very simple drift term, -1/2 there, to make sure that this SDE has a well-defined limiting distribution. And the limiting distribution is simply a Gaussian because we're adding white noise. Okay. So this is a very simple process. We understand the mathematics of this SDE very well. Okay. So now the goal is to reverse the noise corruption process. We want to figure out the time reversal. Okay. So actually, so this problem, figuring out the time reversal of an OU process. So this is a mathematical problem that was solved like 40, 50 years ago. Probabilists have already given us the solution. Okay. So for any given forward process, we can have any predefined drift function. One can derive the analytical form of the backward SDE. Okay, so one can also derive that the drift term in the backward FDE is actually a very, very special function. It's called the score function. So this function, we can think about it as the gradient of log marginal likelihood in the forward SDE. Okay, so if we know this score function, then we can fully specify the backward process, meaning that we can fully specify the dynamics of the process mapping noise to the data distribution. Okay. So now we're going to, so researchers figure out very clever ways to utilize the mathematics to train diffusion models. So it works by simulating the forward process, which is very, very, very simple because we just draw an image from my data set, and then I'm going to add noise gradually to my image. So we have a simulated trajectory of my forward process. And now we're going to try to learn this score function, which is the drift in the backward process. we are going to learn that by doing regression using samples from the simulated forward process. So that's the basic idea, really simple. And once we're done with pre-training, so we have this neural network, right? Now when we want to generate a new image, I'm going to simply plug in my neural network as a proxy to this score function, and then we are going to simulate the backward process, which is going to give me an output image, hopefully from the original distribution of data. So this is really a model with, I would say, beautiful mathematical underpinnings. So we want to understand the theory for diffusion models, why this works. So because diffusion models, we really need to make sure that it has statistical theory, because we are going to use diffusion models not only to generate image and artwork, we also use it for generating protein structures, for drug discoveries, for generating maybe, I would say, design plans or engineering plans. Okay. So there are two important questions here. The first question is, can we show that diffusion models can faithfully learn the underlying data distribution? What can we prove there? Wait. And the second question is, if we already have a diffusion model and we want to generate something new, can we control the generation process to generate something specific to user demands? Okay. So to understand, So to understand the theory, we first need to understand that practical data are low dimensional in nature. Okay. So for example, if we look at that data set of teapots, which are pictures of teapots taken from different angles, although the number of pixels can be like 64 by 64, but the degree of freedom is only 1 because we are just rotating around the teapot, and there's only 1 degree of freedom. Okay, so computer scientists, they figure out ways to approximately estimate the manifold dimension of computer vision data sets. So ImageNet is the biggest one with, I think, with 150 million images. Okay, but by using manifold approximation, it turns out that approximately the intrinsic dimension of the ImageNet manifold was only 43, meaning that every single image in that data set can be mapped to a vector of 43 without losing much information. Okay, so data sets are supported on low dimensional manifolds. So we want to understand, when we use diffusion models to generate new images, can they generate images from the underlying data manifold? So this is non-trivial because you can imagine that even if we have the score function, right, but the diffusion model is going to work by starting from higher dimensional noise vectors, and it's going to go through a random trajectory, and we want to figure out whether the eventual limiting distribution belongs to a latent manifold. Okay, so one has to really look into the mathematics to understand this. Okay, so we actually took a look into this and tried to work out some mathematics. So assuming that my data manifold is linear, okay, a very simple assumption. And we can try to look at the score function, which is the drift term, which is the drift in the backward stochastic differential equation. And turns out that the drift term naturally decomposes into 2 parts, an unsubspace part and an orthogonal part. Okay. And what happens is that in the decoding process of a diffusion model, so the 2 parts are going to have different rate of convergence. And eventually, the overall process is going to concentrate around the true data manifold. Okay. And the similar analysis can be extended beyond linear subspaces, but also to just general smooth manifolds. But the short story is, one can provably show that diffusion models, if they are trained well, they are going to generate sample paths that converge to the true latent data manifold. We also provided some statistical theory because we care about statistical rates for training a diffusion model based on finite amount of data. So the only thing noticeable, I would say the only thing notable here is that the statistical rate of training diffusion models is determined by the latent manifold intrinsic dimension, meaning that this diffusion model naturally adapts to latent geometry and the latent low dimension of data. This is why it generalizes so well. And lastly, we want to ask, suppose we have a diffusion model which can be used to generate something new. For example, in the protein example, suppose that we have a pre-trained diffusion model that can sample from the space of all protein structures. Okay? But now, in order to actually use it, we want to use diffusion models to generate something specific to my target. Okay. And this is already possible. Okay. So in a paper from David Baker's groups last year, so they figured out a way to use diffusion models to generate any protein structure that would bind to any specific target. Meaning that when we do generation, we are not sampling from the overall distribution. We are sampling from a distribution with a specific purpose. Okay. And the mathematical idea is very simple. Because diffusion models is trying to model a distribution, so we can also utilize this to model a conditional distribution. So if I want to generate an image of a dog, then I'm going to put dog as a signal to condition on in my generation process. So we can sample from the conditional distribution of images given that this is a dog. Okay? But however, this would mean that my diffusion model has to model the overall joint distribution between images and their annotations, making the overall pre-training harder. I'm going to skip some slides. So a very, very exciting direction which I'm personally enthusiastic about is that we can utilize the idea of conditional sampling and distribution and diffusion to rethink optimization and decision making. So traditionally, when we think about optimization, we have some decision variable x, we have some objective function f of x, and we have a very complicated landscape that we have to figure out a way to navigate. Okay. But if we have a conditional sampler, then we can say that, hey, if I have a sampler that has already learned the joint distribution between x and y, then I can say that, can you generate a sample of x, given that I want y to have a high value? So we can convert every single optimization problem into a conditional generation problem. Okay. So we work out the algorithm and theory for this. It turns out that this is possible because if we're using diffusion model to do generation, diffusion models naturally adapt to low-dimensional manifold structures, which also means that when we do optimization, we are generating from the same low-dimensional manifolds, meaning that we're actually navigating a much simpler space. And there are mathematical theory which we're going to skip. Okay. And what's more important in practice again, is that we do not want to retrain a full model to learn joint distribution over everything. Usually what we have is we have a diffusion model trained on unlabeled data, unlabeled images, or unlabeled protein structures. And I don't really know what is the optimization objective we want to optimize for yet. So in order to make this practical, we want to work with a pre-trained diffusion model that can sample from the overall marginal distribution of all data points. Okay. And then as we do optimization, we want to only add a little bit of control in the backward SDE. Hopefully, because we are going to steer the generation process and change the output distribution. Okay. And it turns out that this is actually non-trivial. Okay, because diffusion process have to concentrate around the latent manifold. If we add control, like in a way not careful enough, we're going to jeopardize the learned manifold structures. So we really need to figure out a way to add a control to preserve the structure. Okay, so this is something we figured out. One can adapt an external function and external gradient together with a pre-trained score network to make sure that we're projecting the gradient onto the latent manifold so that when we do generation, we're going to maintain fidelity and make sure that new samples remain reasonable. Okay, and we also established optimization theory for gradient-guided diffusion models. So what's really interesting is that one can provably show that in this regime, one can do adaptation, one can do fine-tuning. Okay? It turns out that pre-training can be viewed as a Bayesian prior. And in the language of optimization, pre-training is going to show up as a regularization term in the optimization problem. So if we don't touch the pre-trained diffusion model, we only add additional control, then the best we can do is to find a regularized optimal solution, because we cannot get too far away from the pre-training distribution. But in real-world applications, if we allow online adaptation, if we allow additional self-play and fine-tuning, then this mechanism provably converges to the global optimal solution in the latent data manifold. A very exciting outlook into the future is that generative AI really allows us to sample from a super complicated distribution and to sample and get something that is real but doesn't exist in nature. So this is the beauty of it. So this technology coupled with optimization and control can be utilized for design, for discovery, and decision making. And also, if we allow online adaptation of a pre-trained model, essentially it means that we can keep updating our prior when we have new experimental data. And this foundation model can become more and more knowledgeable eventually. So what I didn't talk about today is that diffusion models actually find substantial applications in robotics because they are very good at modeling joint distribution between trajectories, values, and rewards. People actually use diffusion models to generate new state trajectories with rewards higher than what has been ever achieved. Okay, so we saw that diffusion models already apply to proteins. And also diffusion models and generative AI in general applies to other discovery problems, for example, material discovery. So this was a DeepMind's paper in 2023. So in that single paper, they used a particular generative AI algorithm to discover 2.2 millions of new crystal structures. And they estimated that if humans were to do the job, it could have taken human researchers 800 years to discover all of them and screen them. Okay, so in my own research, we also work on generative AI for genome generation, for designing new mRNA vaccines. We had a paper in which we used, actually a generative language model to come up with new mRNA genome sequences for COVID vaccines. And we were able to achieve 30% more efficiency compared to the SOTA benchmarks. And this 30% was actually validated by wet lab. So all of those are real and they're happening. And there are a lot of very, very exciting theoretical questions to be answered before researchers can keep pushing those fields. All right, thank you very much.
What do you think is the sort of maximum level of approximate dimensionality for the manifold that can be handled?
Theoretically, so for example, in my own paper, we actually showed, I would say, a theoretical bound in terms of, for example, if I use a particular architecture, for example, ReLU layers, then how many neurons do we need for particular manifolds with particular dimensions and particular smoothness? So there are actually theoretical derivations. People can actually analyze how big the models have to be for approximating certain manifolds.
I'm curious about kind of the reinforcement learning paradigms. So for example, in my field, we do some basically drug prediction and we'll generate new drug options. But sometimes chemists will say, oh, that's not possible to synthesize that. So they're giving feedback. So you could imagine saying, like chemists would say yes or no to a particular compound. But do you see any areas where you're able to give more detailed feedback via reinforcement learning? So they could actually go in and say, hey, if you altered this, that would actually be possible.
I think the answer is not only reinforcement learning. The answer has to be in a pre-trained foundation model. So the pre-trained foundation model should have, if it's trained well, it's supposed to have already learned what's possible and what's not possible, because it's supposed to be trained on compounds that people have actually used. And by calling that pre-trained foundation model, and there are ways to measure, for example, the likelihood and whether this newer potential design, whether it is feasible or not. So I think the answer should be to have a really good pre-trained model and a very good and thorough evaluation metrics.